Assalamu alaikum. I welcome you all to another lecture on power electronics. In today's class, we will see the impact of a non-ideality in a capacitor on the performance of the buck converter for output voltage ripple. So let us understand how the equivalent series resistance of a capacitor impacts the choice and value of a given capacitor. So let me draw the circuit diagram for our DC to DC converter. So let us draw the circuit diagram for a buck converter. So a buck converter is designed such that it is operating in a CCM mode, and therefore this will be the waveform for the inductor current. Let me draw it. This is IL. Now this inductor current has a peak-to-peak ripple of which is given between these 2 points. So this is the delta IL here. It also has an average value which is somewhere, we can assume it's somewhere here. So this is the average inductor current IL. Now we design the output side of a buck converter such that DC component within this current of inductor current should flow through the capacitor, and therefore the DC component goes through the resistance only. So this is the capacitor current here, and this indicates that this capacitor current IC is nothing but that is equal to the delta IL here. Now, based on this thing, we do know that the capacitor current, when it is negative, capacitor is supposedly losing the voltage, and when it is positive, it goes on with the increase in the voltage, and henceforth it will have some sort of this type of a waveform across itself. So this is the V naught here, and this corresponds to the delta V naught, which is the ripple present in the capacitor voltage. Now, whenever we design the things, we do know that these values are theoretical, and practical consideration must be taken into consideration before we implement it on a practical scale. So for this given converter, in an earlier class we have deduced that this voltage ripple delta V naught is equal to V naught into 1 minus D divided by 8L C and this F square, where F is the switching frequency as governed by through this switch Q. C is the capacitance, L is the inductance, and D is the duty ratio, which depends on the voltage transformation between this Vs and this V naught. And in terms of the ripple function as a function of the output voltage, this delta V naught over V naught is equal to 1 minus D divided by 8L C F square here. Now this expression of the voltage ripple as a function of the output voltage is solely based on the assumption that the capacitor is entirely ideal, and that is there are no losses within a capacitor. However, whenever we purchase a capacitor, it do have some internal resistance in it, which makes this expression, we need some modification in this expression before we adjust, or we choose a value of a given capacitor. So the capacitor model, a non-ideal capacitor model, has series resistance in it. Therefore, this model characterizes the capacitor as this given circuit here. So we have this capacitor C here. So here we have the delta IC, which is equal to nothing but that is equal to delta IL. It produces a voltage delta V naught C, and this delta V naught C is this delta V naught, which is available in this given expression. However, if we include this value of this RC, then this RC shall have its own output voltage ripple, because it's a series component. So whatever the current is flowing through this capacitor will also flow through this resistance, and thereby it will create a voltage across this resistance, and together we will see that they two will sum up with each other, and thereby it will increase the output voltage ripple based on this given expression here. Now, to further understand this given concept, let us do an example to elaborate this thing. So, for this example, let us assume that we have an input voltage equals to 3.3 volt and output voltage equals to 1.2 volt. We assume that the inductor is in a CCM mode and that the delta IL is equal to less than or equal to 40% of the I naught here, and this I naught is set to be equal to 4 ampere. We also assume that if when we are designing this given converter, we want to ensure that this delta V naught is less than equal to the 2% value. So we need to now identify a few things before we can finally put in the values in this expression to find out the value of the capacitor. So based on this thing, the duty ratio D is equal to V naught over V in, and that turns out to be equals to 0.364. We can further identify, because this is I naught is equal to 4 ampere, and we are assuming that this IL is nothing but that is equal to this I naught, which is flowing through this resistance. So therefore, 40% of this 4 ampere will give us 1.6 ampere. And now the next thing is to find out the value of the inductance, because that is also part of the procedure in finding the value of the capacitor. So the inductance L is equal to it is equal to Vs minus V naught divided by delta IL into Fs, and let us assume that this Fs is equal to 500 kilohertz, right? So in my earlier lecture, I have already explained how we have concluded this value for the inductance L. So multiply by the D, it gives me something around 0.9555 microhenry here. So now that we have the value of the inductance available, we can simply substitute the values to find out what is the value of the capacitor C here. So capacitor C is given as C is equal to 1 minus D divided by 8 L into delta V naught over V naught into this F S square, and this gives me a value 0.16 microfarad here. Now this value of 0.16 microfarad will suffice the purpose in all the simulations unless and until we add in the non-idealities in the system. But because we want to practically create a circuit of a buck converter, we will get something of this nearby this more than or near or equal to this particular rating, and that comes along with the data sheet. So data sheet must specify the amount of the equivalent series resistance present for this much amount of the capacitor available here. But before that, we need to establish that if we want to have a very stiff requirement of not exceeding the delta V naught equals to or less than or equal to 2%, then we need to specify what is the maximum value of the ESR we can afford to have in our practical capacitor. So for that, we will write this as delta V naught, that is equal to RC into delta IC here, and delta IC is, by the way, what it is equal to this delta IL. So that becomes equal to 1.6 into RC, that is equal to delta V naught. And if we substitute the value in here, we do know that the delta V naught is equal to it is equal to 2%. So it is 2% of the output voltage 1.2, and that turns out to be equal to 24 millivolt here. So if I make it equal to 24 millivolt, then this is RC becomes equal to 15 milliohm here. So this means that if I want to create a buck converter and I want to have a practical application of a buck converter, this 0.16 microfarad is one expression of selecting a capacitor, but I have to ensure that whatever capacitor I am using practically, it has an equivalent series resistance of 15 milliohm or less. So sometimes what happen is, because this ESR value is usually an inverse of the capacitor rating or capacitor value. So sometimes we want to ensure that the ESR is limit ESR is well below the calculated range. So sometimes instead of using 0.16 microfarad, we go for a much higher value of a capacitance to ensure that this delta V naught stays always within the 2% limit. So that's all for the today's class. I thank you very much. Allah Hafiz.